If the operational amplifier is the most useful integrated circuit in the analog designer's arsenal, then one could make a very good case that the operational transconductance amplifier comes next in line in terms of usefulness. And when it comes to implementing voltage control of parameters, it's even more useful than operational amplifiers, as we will see fairly soon. When I first began using the Operational Transconductance Amplifier, which from now on I'm going to call an OTA because Operational Transconductance Amplifier is just too many syllables, the standard symbol that was used looked like this. Now you may note that this is very similar to the standard operational amplifier symbol. It has an inverting input, a non-inverting input, an output, but now note one difference here is the output of the OTA is not a voltage, but a current. We'll talk at length about that later. In addition to these two inputs and the output, it has a third input called the amplifier bias current. We will talk about this at length as we go through the next few videos. This is a current input, not a voltage input. This is the input that makes voltage control very easy to achieve. The problem with this symbol is that it's fairly easy to confuse the amplifier bias current input with a power supply connection. If you recall, when we drew power supply connections on an operational amplifier, typically they came out of the top and the bottom of the two angled sides. So you could perhaps confuse that with an operational amplifier power supply. More recently, this symbol has been modified somewhat to avoid this confusion. And note that now the amplifier bias current input comes in right at the output of the symbol. And here I have explicitly shown the two power supply connections. Now again, typically this is powered by bipolar supplies, say plus and minus 9 or plus and minus 15 or whatever, but there's no reason it has to be powered on bipolar supplies. In fact, I have actually seen a design for a voltage controlled amplifier where the voltage control was implemented by dynamically changing the negative power supply voltage, which was kind of a neat little trick. We might look at that later. Just as with operational amplifiers, we usually do not show the power supply connections. So generally you would just see the two inputs, the output, and the amplifier bias current. As we will see shortly, in modern OTAs, there is usually yet another input. This input is called the diode bias, and it is designed to linearize the input. We'll talk at length about this later, which bottom line helps improve the signal to noise ratio. This is typically shown as two diodes right on the symbol between the two inputs, with the diode bias going right in the middle like this. Now again, remember that the inputs are voltages, the output is a current. What is actually amplified is the difference in the two inputs, the non-inverting input voltage minus the inverting input voltage. We'll discuss this in more detail very soon. Often one of the two inputs is grounded, so you've just got a single voltage input, and depending on which one is grounded, you can either have an inverting amplifier or a non-inverting amplifier. The gain of this device is defined as the output current divided by the input voltage. Now again, that input voltage is the difference in the non-inverting and inverting input voltages. And this parameter, I out divided by Vn, is called the transconductance, G sub m. Note that I over V is the reciprocal of resistance, which is conductance. So we have a conductance, but it's across that device from the input to the output, thus trans. Therefore, it's called a transconductance amplifier. The key to the usefulness of the OTA as a voltage-controlled device has to do with the amplifier bias current input. And this is because the gain, G sub m, the transconductance, is equal to approximately 19.2 times the amplifier bias current. So by changing that current, you change the gain of the device. Now that equation, 19.2 I sub ABC, does make a few assumptions. First of all, it assumes that you are not using the linearizing diodes so that the input labeled I sub D is simply not connected. That's item number one. Item number two is this assumes that you're at room temperature and the temperature is not changing. We will look at this relationship in somewhat more detail in a later video. Now note that in general it's fairly easy to convert a voltage to a current. For example, you could do something as simple as just use a resistor from your voltage to a known voltage and that will give you a current. So it's fairly easy to convert a voltage to that amplifier bias current. Now, depending on how fancy you want to get, that current conversion can get a little bit more complicated than just a resistor, and we'll see some circuits that do that later on. Now also, your output is a current, which is perhaps not the most convenient form, but again, it's pretty easy to convert a current to a voltage. Again, you can just use a simple resistor followed by some sort of a buffer, or you could use an inverting amplifier with a simple resistor in the feedback loop, and all that current squirts through that resistor and converts that current to a voltage, and you can scale that by adjusting the value of that resistor. We'll look at various ways of accomplishing that current to voltage conversion later, but needless to say, that's not a difficult thing to do. Now, as I mentioned, there are some advantages to using the diode bias input in terms of improving your signal to noise ratio, but that's going to have to wait until a later video. That's enough for this one. In our next video, we will continue discussing the basics, including a little bit of history of the device and the types of devices that are actually available.